Hello everyone, welcome to the course on architectural design of ICs. So, till now we have seen different kind of architecture of the various operation like this multiplier, then a divider, then adder. So, all these structures, how we can design efficient architecture in corresponds to the that is speed, power, area as a major constant. We have seen the architecture till now. Now, we will see some of the very basic circuits, how to actually if they have been asked in the that means interview, or they have been asked you to design that circuit. So, at that time how to start with the corresponding circuit. First focus on what is the problem, and then from that particular point we will start doing by step how to solve the problem. So, we will see very basic design tips and tricks for the very basic circuits, very basic digital circuits by which we can implement any complex circuits. So, the very first thing is that suppose the one of the major that means circuits which is being mostly used in digital circuits, that is the multiplexers. So, using multiplexers I can implement any circuit, So, how any circuit? Basically using multiplexer I can design the AND gate, NAND gate, OR gate or NOR gate, inverter. So, any gates, or I can implement XOR gate, I can implement this flip flops using multiplexer. So, we will see that how to design this. Let us first consider this case, which is how to convert one multiplexer into a NAND gate. So, to start with that, at the very beginning what we have to do, that means the NAND gates, the truth table for NAND gate is that when all this A actually is suppose A and B both are 0 0, 0 1, 1 0, for all this case the output should be 1, and for 1 1 they should be 0. So, if we consider the particular expression, logical expression for 1 2:1 multiplexer. So, at that time if I consider the two input as A and B and the select line as the S. So, at that time I can write the output expression will be out equals to A S plus B S bar. Okay. So, now what I need is that I need this particular expression should be work as a NAND gate. Okay. So, to actually to perform this particular task into one NAND gate. So, what we have to do is that at that time this, now if I just draw the corresponding 2:1 multiplexer. So, we will be having this. So, this is my select line, this is A and this is B. Okay. So, now what I need is that I need A B this bar. Okay. So, whenever I need this A B bar, so at that time what I can write is that here suppose at this particular terminal, if I provide this as or A B bar, I can write that as A bar plus B bar. Okay. So, if I just write this particular terminal as okay. So, here let us say this is A, this is 0 and this is B bar. So, at that time what will happen? Now, this A, the A signal is now that is sorry not this one is will be 1. So, now instead of this A, if I provide here as 1, so suppose not this one, this will be A S bar and B S. So, if I provide this particular terminal as 1 and this select line as A. So, at that time what it will be? It will be A bar plus, and here what is that? Here actually as the input we provide as B bar, and A is already, this is for 0, this is for 1. So, A is already 1. So, it will be 1. So, this is A bar plus A bar plus B bar, that is nothing but A B whole bar. So, that means this expression now I can write as the NAND gate. Okay. So, in this manner, if I want to implement this particular function to any other gate, so according to this particular logic, now you have to put what value will be at 0, what value will be at 1, and what value will be at select line. Okay. So, now I can see, or I can say that okay, now depending on the corresponding logic, which is this, now the output will be, that means if I draw, so at that time it will be at 0 terminal, it will be just at 1 terminal, it will be, if whenever this is A means this will be just A B I just want to implement this. So, as this is A bar plus B bar. So, and according to the logic it is A S bar, sorry, B S bar plus A S. So, in the A what I will do, I will provide B bar, and here I will provide 1. So, it will give me A bar plus B bar, which I can write as A B whole bar. Okay. So, this will be the, now this particular multiplexer, now it will be act as a NAND gate at that time. Now, let us consider another example. Okay. So, where I have to design this particular multiplexer should be work as a XOR gate. Okay. So, in XOR gate, the corresponding logic for XOR gate is what? This XOR function says that it will be A bar B plus A B bar. Okay. Now, what I have to do, this multiplexer I need to be work as this XOR gate. So, according to the multiplex, that means multiplexer logic, what is that? That is A, actually if I select, if I mention that okay, select is my A. So, at that time this will be A B bar plus A bar, and here it comes under B. So, that means at 0 signal I provide the B, where A bar B, and for this one terminal it is providing B bar. So, A B bar. Now, this is nothing but A XOR B. Okay. So, that means the same multiplexers, just by changing or by putting different values to its input and to the select line, I can make this multiplexer to be work as a XOR gate. So, in the previous case, whenever we have just applied 1 and B bar along with the select line as A. So, at that time the same multiplexer is working as a NAND gate. Here this, with this particular configuration, the same multiplexer now it is working as a XOR gate. So, it is not that it is only confined to that you can implement only XOR gate and NAND gate. It is not like that. Using multiplexer with different configuration at this particular inputs and the select line, you can make these XOR gates to be work as OR gate, you can make this XOR gate to be work as a NAND gate, any gates. Okay. So, all the gates you can implement using these multiplexers. Okay. Now, we will see how to implement the half adders using multiplexers. So, according to the logic of half adder, what we need is that we need to implement the carry, we need one AND gate, and to implement the sum we need one XOR gate. So, in how to implement the XOR gate? The XOR gate can be implemented by using this A and A bar at the inputs and B as the select line. You can just do the reverse, B and B bar here with select line as the A. Then how to implement this particular function as AND gate? So, if I provide this as 0 and the other input as A and B, that means when that will be act as a AND gate? The AND gate, when it will be act as a AND gate? For out logic, this is A S bar plus, let us say, okay, not A, consider a different value, suppose P S bar plus Q S. Okay. So, now if you for this particular case, when this S is 0, so at that time if you make this as 0, so it will be 0 plus Q as B and S as A. So, it will be act as a AND gate at that time. So, that thing has been implemented using these multiplexers, and the XOR gate can be done either you can use B and B bar over here and A here, the same it will be act as a XOR gate. If you provide A bar at this input line and B at the select line, again it will work as a XOR gate. So, that means now using 2 multiplexer, 2:1 multiplexer with this type of configuration, now I can implement this as a, which will be work as a multiplexers. Okay. So, now let us consider another example how we can make this multiplexer to be work as D flip flop. Okay. So, D flip flop means actually it has to store its value. So, now whenever we are having this particular, actually if we do not consider, okay, if I consider only this, or if I just want to, that means if I just ask you to implement this multiplexer as the latch. So, at that time what it will be means the output again it will be connected to this, and the select line will be your corresponding clock signals, and this is the D input. So, this is nothing but one latch example. Okay. So, that means whenever this clock signal is 1, so at that time the D will pass, whenever this clock signal is 0. So, at that time this output will again it will come to its that means to its input. So, now in flip flop we are having this, actually this is the example of latch using 2:1 multiplexer. Now, whenever we are having this that flip flop we have to design. So, at that time we can connect that another 2:1 multiplexers, where this input is, that means sorry, this input is connected here, and this is also another latch which is connected, and here the clock is just inverted one. That means, this is nothing but the master slave connections what we did using, that means this using SR latch, whatever we developed the, that means master slave JK flip flop, that means the D flip flop. The same configuration here we have used to implement using 2 latch which has been generated or which has been designed using 2:1 multiplexer. So, that configuration we have used to implement the D flip flop using multiplexers. Okay. Now, then again, if the question has been asked to make this as T flip flop. So, the D flip flop we already make. Okay. So, then again actually T flip flop means we have to the D flip flop, the output from the D flip flop, that will be just inverted and it will go to the D input of the corresponding flip flop. So, D flip flop using this corresponding this 2:1 multiplexer we have already designed. Now, we will have, we can put, if we are having this control signal. So, at that time whenever this T is 1. So, at that time it will be just act as a inverter operation, which will be at that time this particular flip flop will be just be act as a T flip flop. Okay. So, instead of XOR gate, if you can just make this as only one inverter without this T input. So, this will be the T flip flop made by 2:1 multiplexers. Now, if you do not have in the library, again if you do not have this inverter operation. So, at that time the multiplexer itself you can make that as a inverter and you use that particular that means multiplexer over here to make this D flip flop to be work as a T flip flop. Okay. So, these are the very basic circuits which is, that means using multiplexer only you can implement. And in actually in FPGA we know that FPGA all the logics are basically implemented through multiplexers only. So, how these multiplexers, as we have discussed or as we have already seen, that multiplexers can implement any function, that means any this logic gates. So, definitely I can use these particular fundamentals while I am designing one particular FPGA based circuit design. Okay. So, then we will see another example which is very basic circuit for this edge detector. That means, whenever what is this edge detector? Whenever this clock edge occurs, so at that time it will detect that okay, there is one edge of the clock which is happening. So, how to detect? Actually, there will be this rising edge, there will be falling edge of the clock, and you can also detect that rising and falling both altogether. So, the first circuit is basically related to the rising edge detector circuit. So, what is this is that, so we are having one D flip flop where the input is basically ANDed with the inverted of its Q output. So, then if I just make this particular circuit, that means make this configuration. So, at that time what will happen? Suppose this is the clock signals or the clock waveforms which is running like this, and the corresponding D input is, let us say, is something like this. So, when actually this rising edge, when it will detect is that, suppose at this particular edge, as this is D flip flop, at this particular edge it will find that okay, what is the value of D. Now, the value of D is already 0, then up to this we have to make what will be the corresponding Q output. Okay. So, if we just draw that okay, this is my clock signal, okay, and the D is basically, let us say, up to this, and then we are having up to this, and then we are having then. So, this is my clock, this is my D input. Now, what will be the corresponding value at Q? So, the Q signals will be, so at this edge, at this edge, at this edge, and at this edge. So, at this particular edge, as this value is D value is already 0. So, it will continue to 0, and again it will continue to 0 up to this, and here it finds that okay, this Q value is D value is 1. So, again it will start 1, and here at this edge it finds that okay, the D value has becomes to 0. Okay. Then again it will continue, then again here it will find 1, and it will continue like this. So, this is nothing but the Q. So, when this Q, then this is basically inverted of Q. So, inverted of Q means this is now 1, this particular is 0, this is again 1, this is 0. Now, within this now this is my, if I say that okay, this is the Q bar. So, this is Q bar. Now, depending on this D input and the Q bar, if I just as they are ANDed. So, at that particular instant, at this particular instant both are 1. So, there will be 1 1, rest of the case it is 0, then again it is 0, and here whenever this, that means for this particular time period both are 1. So, that means again I will get 1 pulse over here. Okay. So, that means it finds that okay, whenever there is this rising edge of this and rising edge of this, it is creating one pulse, this is creating one pulse which says that okay, that this D input is of rising edge. Okay. So, that means this is the edge detector circuit, which edge? Positive edge, sorry, not positive, or I can say that okay, rising edge. Okay. So, now in the next, if I want to detect the falling edge, that means when this particular data is falling. So, at that time what it will be its corresponding architecture, or what will be the circuit which can detect the falling edge of the data input, okay, or the signals which is appearing over here. So, at that time, so in falling edge what we have to do, in earlier case what was there, the inverter was placed over here, the data input was coming there, but here what I did, I just placed, I just interchange this position of inverter in the upper path. So, at that time what will happen, at this particular edge, this negative edge, it will give me one pulse, and again at this particular edge it will give me another pulse. If I just draw again, if I draw the Q, and this will be the Q bar, if I get. So, in earlier case this was creating the pulse, this was creating the pulse when there was positive edge. As I make inverting of this D, so that means at that time what will happen, the 1 will become 0, 0 will become 1. So, at this time this the falling edge will be detected and it will give you the pulse at this detector output. So, using this circuit now you can detect whether there is any falling edge of your signal. So, this signal is, this particular circuit is falling edge detector circuit. Now, I need, that means both the edge should be detected at the output. Okay. So, then how to do that? That can be done using, if I use, instead of this, here what we are doing, here we are doing, if I say that, okay, this is what, this is d into q bar. Okay. So, this is used for positive edge, sorry, rising edge, and for this, what is this? In this case, this is d bar q. So, when I need to combine both together in the particular circuits, so at that time, what I need? I just need to add them. So, if I add them, d q bar and d bar q is nothing but d XOR q. So, that has been done over here. So, these particular circuits now it can detect both the, that means this either of this rising edge or this falling edge. Okay. So, if you just write the Verilog code of this and then if you can run, then you can say that, okay, if there is a change in this, whether that is change means whether that is 0 to 1 or 1 to 0, you always get one pulse depending on the corresponding structure what we have already designed over here. Okay. So, this particular circuit is used, suppose for one such application you need to detect this edge, that means whether there is any event at the corresponding input signals. So, that you can just detect using this kind of circuit. So, one for the rising edge, another for the falling edge, and this particular circuit for rising and falling both the things. So, thank you for today. Again we will discuss some other basic building blocks, how to design them in a efficient way. Thank you for today.